Hello everyone. In this lecture, we will discuss about convolution operation. That is a very important operation in LTI systems, as you know, in the course of signals and systems. So let us start with the discussion on convolution operation. We will basically see that what does a convolution operation mean, and so convolution operation. Convolution operation. Now, let me tell you that convolution operation essentially requires two signals or two functions. That is basically, let us consider there are two signals, x1 of t and x2 of t. So convolution is performed between these two signals, and convolution operation happens between these two signals in LTI systems. So essentially, we also know that a general form of an LTI system where x of t is the input that is given to a particular LTI system, h of t, and we get the output y of t, and we know that the output y of t, that is essentially the convolution between x of t and h of t. This is how we denote convolution. This is how we denote convolution. And here, what we were talking about just now, that we need signal number 1 and signal number 2. So in our case, we have our signal number 1 is x of t, and our signal number 2 is our impulse response of this LTI system, h of t. Okay, so this convolution operation, we know that everyone must be knowing very famously basically the integral operation that is performed in the manner. Essentially, we have x of tau, h of t minus tau, d tau, when it is integrated from minus infinity to infinity. This is known as that we have performed convolution between x of t and h of t. This is a general mathematical notation, mathematical definition, mathematical formulation of convolution. Okay, so this is essentially the mathematical formulation of convolution. We will discuss that what basically this mathematical operation signifies here. So the first thing we will see that basically convolution is, we'll write down the definition here, and this definition has been taken from the book Opinium. Check this. Convolution, basically convolution, I'll write down the definition here. Convolution is an integral that expresses the amount of overlap, the amount of overlap okay, of one function when it is shifted over another function. When it is shifted over another function. Okay, that is the amount of overlap of one function when it is shifted over another function. Okay, you can see that we have various significant terminologies here. The first thing is that we have integral here. A convolution is an integral. Okay, a convolution is an integral that expresses the amount of overlap. It expresses the amount of overlap, which means that we have two functions and we are essentially interested in the overlap of one function over the other function. We are essentially interested in the overlap of one signal over the other signal that we have, essentially of one function. Let us say we have our one function is x of t, that is we are having here. Let us consider the case of this LTI system only, where one function is x of t and another function is h of t. So h of t is the impulse response. So one function, when it is shifted over another function. Okay, so for our notation purpose, let us consider it to be h of t only. Okay, let us consider it to be h of t only. So because the way we are essentially, either we can consider this one function to be x of t or h of t, and anyone we can consider. Let us consider for this case, this is h of t when it is shifted over another function. Let us say that our another function is x of t. So what is happening is that basically in convolution operation, we encounter 5 different operations that we study in signals and systems. What are those 5 different operations? The first operation, you know, that we have already studied is shifting. The second operation, you know, that we have already studied is scaling. The third operation is differentiation and integration. I'll consider here integration, and let's say differentiation. And the fourth operation that we study is, because I have put integration and differentiation together, so now we have only 4 operations. The fourth operation is convolution. We'll see that how this fourth operation, particularly this fourth operation, this convolution, this makes use of the earlier 3 operations that we have seen. Okay, so essentially what happens is that we have 2 signals, x of t and h of t. We basically shift one signal over the another signal. So one signal that has to be shifted, let us consider it to be h of t. Okay, this is going to be shifted. So the other signal over which it is going to be shifted is going to be fixed. So what we'll do is that we will fix this particular signal and we'll shift this particular signal over x of t. But directly we will not do. Before that, what we do is that we just replace this variable, this independent variable time, with a dummy variable, let us say tau. So x of t becomes x of tau and h of t becomes h of tau. And now we basically fix this particular signal, that is our x of tau. And we are going to shift this second signal over our x of tau. So how we are going to shift this particular signal? The first thing, the second, let us say this is the first operation, that is basically changing the independent variable, that was time, with replacing the independent variable time with a dummy variable, that is tau. The first operation was that we made here t is equal to tau. The next thing we do is basically a time reversal operation. Okay, so the time reversal operation, and time reversal operation, as we know, that it is a special case of scaling. We essentially scale that signal with -1. Okay, scaling operation is, if I do this is just a signal for an example. If I'm performing scaling here, so this is x of a t. This is what we do when we scale the signal. So essentially when a is equal to -1, So we say that we have performed time reversal operation on that particular signal. So when we do time reversal operation, this becomes h of minus tau. Okay. And the next thing we do here is time shifting. The next thing we do here is time shifting. How? This tau is shifted by tau minus t. So this essentially becomes, when I replace tau with tau minus t, this becomes tau t minus t, h of t minus tau. Okay. This time shifting we perform. So you can see that we have performed two operations already here. That is scaling and shifting. These two operations we have already done here. Now the next operation that we are going to do, I'll write it here, that is multiplication. Multiplication of what? Multiplication of h of t minus tau with our fixed variable, fixed signal, this fixed signal that was x of tau. So we do multiplication. And finally, we make use of our integration. The last operation we do is integration. And when we do the integration, we get here x of tau, h of t minus tau, d tau from minus infinity to infinity. Okay. This is the entire convolution operation that involves the application of shifting, scaling, integration, multiplication, and in the manner that it requires these operations, in the manner that it involves these operations that I have enlisted here, that one of the signals will be fixed and the other signal will be shifted, and then it will be time scaled, and then it will be essentially multiplied with the fixed signal, and then it will be integrated. And finally, what we will obtain is basically the convolution, and that convolution is nothing but the operation, the mathematical operation that expresses the amount of overlap of one function, that is h of t in our case, when it is shifted over another function. So we want to shift h of t over x of t. And for shifting h of t over x of t, we are essentially performing all these operations: time reversal, time shifting, multiplication, integration. All these operations are intended to basically shift that h of t over x of t. And we'll see how that happens. That can be seen with the help of an example only. So we'll solve an example for this particular case. Let's say that I'll consider suppose I have a signal x of t, and this x of t is given as this one.
Happy Holi, sir.
Happy Holi.
सर पेपर का काम भी कभी
हाँ तुम मतलब वहां से प्लेगरिज्म का चेक कर लोगी ना वहां से?
हाँ ठीक है,
वो कर लेना, बस वही करना रहेगा तुम चेक कर लो, और अगर कुछ चेंज करना होगा तो वो भी करना पड़ेगा। मैं तो मतलब फिगर और रेफरेंसिंग चेंज कर दूंगा, उसके बाद अगर प्लेगरिज्म ज्यादा होगा तो फिर उसको देखना। हैप्पी होली। हाँ। घर में सब
Yes, sir.
Okay, so we have the first signal as x of t, and that is just a minute. Let us make a proper signal only. So suppose we have so let us say that from 0 to 2, 1.
या वो गर्म नहीं रहा क्या?
हाँ,
गर्म नहीं रहा, पसीना पसीना हो गया।
अरे ऑन कर दो तो सर्दी हो जाती है।
अरे क्लास में
नहीं नहीं ठीक, क्लास में चल रहा था, रिकॉर्डिंग चल रही थी। एक मिनट।
गिफ्ट जब हो 16 है 15 है
इसमें 15 ही डाले हैं मुझसे।
ओके थैंक यू।
वो कल ही मीटिंग कल हुई थी ना, इसीलिए।
अच्छा अच्छा
Okay, so we have this from, this is our signal, that is x of t here. This is the first signal that we have. And let us say that the impulse response that we are having. So we have the impulse response, that is h of t. This is 0. Let us say the impulse response is having this kind of waveform. This the signal value is 1.0 here. Here also it is 1.0. Okay. Now we have to find out. Basically, this is an LTI system again, and we have to find out y of t, that is nothing but our x of t convolving with h of t. Okay. So okay, now we'll perform the steps. The first thing that we do is that we basically change the, here it is time and here it is time. So basically we change the independent variable time with a dummy variable tau. So this becomes x of tau, and here we have 0, 1, 2, and this is 1.0, and here we have this as 1, 0, 1, and this is varying now with h of tau. So this is the first thing we do. Now the second thing what we do, we basically do the time reversal of this. The first signal we'll fix, this one we'll fix, and this one we will overlap or move over x of t. That is what we are going to do. So the first thing, in order to do this moving and overlapping from job over the x of tau, what we will do is, the first thing we do is that we perform the time reversal of this. So when we will find out h of minus tau, this will become will vary from 0 to or better from -1 to 0. Okay. Then the next third step, what is the third step, and that is the important one. The third step, what we have here is what we do here is tau minus t. That is what we do here. So essentially, we say that we are delaying this h of minus tau by t time units. We are delaying this time reverse signal by t time units. Now, we are delaying it by t time units if t is positive. Okay, if t is positive, so tau minus t will be having some here, since it is negative, so tau, suppose t is equal to 1, so this will be minus of tau minus 1, so this will move ahead in this right side direction. But if t is negative, that means that if t is less than 0, so what will happen, that this signal will be advanced, because we will have here minus of tau plus something. Suppose we have t is equal to minus 2 here, so this will be minus of tau plus 2. So when we have minus of tau plus 2, so that means that the signal will be shifted here from here. Suppose here we have it as plus 2, so this will be varying from -2 to -3. Okay, so we now, for this particular signal, this particular shifted part, this is basically t minus tau, h of t minus tau. Now for this we will take different cases. So the first case, okay, the first case, the case number 1. Case 1 is when t is less than 0. I take the condition when t is less than 0. So what will happen here? When t is less than 0, as we just discussed, we have here h of t minus tau, and this signal that is varying from -1 to 0, this will move from t minus 1 to t. Okay, that we can see here. This will be the signal where it is going. Okay. Now what we have to do, we have to multiply x of tau with h of t minus tau. So basically we will multiply x of tau with h of t minus tau. Remember that we are doing it for the case of t minus t is less than 0 only. So when we multiply, we can see that just simply multiply. Here you can see that x of tau is varying from 0 to 2. And before 0, it is having no value. And after 2, it is having no value. And here h of t minus tau is having value from t to t minus 1, or whether t minus 1 to t, whatever this part. This is basically the values where h of t minus tau is lying. But after t, after this point, this entire part, h of t minus tau is essentially 0. In this entire part, h of t minus tau is equal to 0. Here also and here also. So when we multiply both of these, this multiplication will come out to be 0. And in that case, for that case, I write here y of t, that is essentially the integral of from minus infinity to infinity x of tau, h of t minus tau d tau, that becomes equal to 0. Okay, so that was the first case. Okay, I take the second case now. The second case, maybe we can take a new page. That is the case 2. The case 2 is that let us say that if t is greater than 0 now, and it is still less than 1. Okay, because our x of tau, remember that it is varying from 0 to 2. Okay, so we'll take one by one. Suppose t is some value that is greater than 0 and some value that is less than 1, 0.4, 0.3, 0.5, 0.6, any value. Okay, so how our h of t minus tau will look? So our h of t minus tau will look like we will have this kind of waveform. Okay, and here where this is basically t only, and this is t minus 1. Since this t is greater than 0, so this t will be greater than 0. But since this t is less than 1 also, so t minus 1 will be less than 0. Okay, like this will be like. And our x of tau. What is our x of tau? Our x of tau is varying from 0, 1, and 2 tau. Okay, so it's tau. Okay, now you can see that this t is less than 1. Okay, and this t minus 1 is less than 0. Okay, so when we multiply both of them, x of tau and h of t minus tau, this is how this is going to overlap. You remember that initially this was somewhere here, now it moved to this part. Initially it was somewhere in this region, now it has moved to here. Okay, so we'll see that how much it is overlapping. Initially it was not at all overlapping, it was somewhere here and it was not overlapping with x of tau. Now it has moved to this part and it is now, we'll see that how much it is overlapping. Okay, so I have this axis. We'll do one thing. We'll make use of some colors. Let us say with red color, I'll denote x of tau, and with blue color, I'll denote h of t minus tau. And this product we are seeing. Okay. So basically now I'm talking about, let us say x of tau. So x of tau is going to vary from 0, 1, and 2. And then the next thing we have is h of t minus tau. H of t minus tau is varying. You can see this here somewhere t is there, that is less than 1. And somewhere this t minus 1 is there. Okay. Now we need to see that how much it is overlapping. So the overlapping part that I'm going to denote with purple color, let us say. This is basically the overlapping part. Okay, this is where it is overlapping. From 0 to t, in the interval 0 to t, it is overlapping. Rest everywhere here from 0 to t minus 1, h of t minus tau is having some value, one value. This amplitude is 1.0 here. This amplitude. Here also it is 1.0. Here also it is 1.0. So this amplitude is 1.0 here. But from 0 to t minus 1, h of t minus tau is there. Okay, but x of tau is 0. From 0 to 2, x of tau is present, but h of t minus tau is present from 0 to t only, where this t is less than 1. So we have essentially, this is the only part where it is where h of t minus tau is overlapping with x of tau. Okay, so when I try to calculate the integral, that is x of tau multiplied by h of t minus tau d tau from minus infinity to infinity, let us say take it this only. This is basically y of t for the region t when it is greater than 0 and less than 2. So we can see that here what we will get from minus infinity to 0. You can see from minus all the way from minus infinity. If I go to minus infinity, all the way from minus infinity up to 0, this is going to be 0. Okay, from 0 to t, it is going to be 1. Read out, and plus from t to infinity. Okay, from t to 2 also there is x of tau present. From t to 2, from t to 2, x of tau is having a value this 1, but h of t minus tau is stopping over here only. It has a value till t only. After t, h of t minus tau is not having any value. So that is essentially 1 multiplied by 0, that is again 0. and same for further after 2 also. Both of them are not having any value. Both of them are having 0 value. So basically we have here from t to infinity, I'll directly write, and 0 d tau. So we get here, this is 0, this is 0. Here we get, you can see here that the integral will be tau and t minus 0, so that will be t. So y of t is equal to t for time greater than 0 and less than 1. Okay. Now for the next part, this third case is when, case number 3 is when we have, let us take t greater than 1 and less than 2. T is greater than 1 and less than 2. Now let us see that from where to where our h of t minus tau is going to slide. This is basically, it is sliding only. Okay, so t is greater than 1 now. So we have 1 here. Let us take this as 2 here. Okay, t is greater than 1. So our h of t minus tau is varying from t minus 1 to t. So we'll have t lying somewhere here, and t minus 1 would be lying somewhere here. Okay. And this will be this kind of square waveform. Just forgive me for my bad drawing. This is just a simple square waveform. Okay. Try to make it better. So this is what we are having here. This is essentially our t minus 1. This point is t minus 1. Okay. And the second signal, that is our fixed one, that is x of tau, that already has a value. We know that it has a value from 0 to 2. We have 1 here. Okay. Now let us see the multiplication between the two. Okay. So the multiplication between the two now, x of tau, x of t minus tau, this multiplication, what it is going to be now? Now we have, I'll again draw. I should have made it in the previous combination of the colors only, like I had done before. So I'll do it in the same manner. Let's say that I'll denote x of tau with red. Okay, x of tau. First I will draw x of tau. So x of tau is this 0 to 2. Okay, and or let us make it a little broader. X of tau is this 0 to 2. Okay, and then we have this thing that is from t minus 1. Here somewhere we are having 1 also. The second thing is h of t minus tau. That I'll make with blue. Okay, so h of t minus tau. This t minus 1 is where somewhere here. This t is somewhere here, and this is the area where it is overlapping from t minus 1 to t. Now this time the output signal y of t, that will be the integration of the product, this product. Okay, so x of tau, h of t minus tau, d tau from minus infinity to infinity. And we have basically, now you can see that the only area where we will have some non-zero value is from t minus 1 to t. Rest everywhere we are going to have 0. So from minus infinity to 0, we are already having no value. There is 0 only. From 0 to, okay, I'll bifurcate in from minus infinity to 0. This is already 0 d tau, plus from 0 to t minus 1, 0 to t minus 1, again we have x of tau 1, but h of t minus tau is 0 d tau. Okay, then we have from t minus 1 to t. So t minus 1 to t, we have x of tau also 1, h of t minus tau also 1, d tau plus from t to 2, if we see from t to 2. So from t to 2, we will have essentially, you can see that this is going to be having this x of tau is having value 1, h of t minus tau is having value 0, d tau. So essentially, we will be left over with simply 1 d tau from t minus 1 to t, and that becomes equal to, now we get here, what we get here, tau and t minus 1 to t, that means we get here t minus 1, so this becomes plus, so this becomes 1. Okay, this is y of t. So from in the region when t is 1 to 2, y of t is having a value 1. Okay, you can see in the previous cases we have basically what we have done. We took t from initially we took t for less than t less than 0. That was our first case. The second case was when t was lying between 0 and 1. The third case is when t is lying between 1 and 2. Okay, so y of t is equal to 1 for t lying between 1 and 2. Okay, now the fourth case we have, and that is the last case. Case 4, we have that when t is lying between 2 and 3. Okay, so now we'll see what will happen with h of t minus tau. You can see, so we have h of t minus tau. Okay, this varies from t to t minus 1. I'm sorry, t minus 1 to t. So we have one mark as t minus 1, the other mark is t, and basically we have essentially we have here, you can see that this is varying from, now t is greater than 2. So t minus 1 will be lying somewhere less than 2. So here suppose 2 is there, so this will be less than 2. And t is less than 3, so t is here, so we have 3 somewhere here. Okay, so this is our h of t minus tau, which is varying from t minus 1 to t minus 1 to t. And the other signal, that is our fixed one. So that is x of tau. So this signal is having a value from 0, 1, 2, and tau. Okay, so now I'll take the product between x of tau and h of t minus tau. So we can see that we have here, again I did, okay, now this I'll make with red and this I'll make with blue. So let us make x of tau, so that is from 0, 1, and 2. Okay, and let us make h of t minus tau. So before 2, there is a point which is t minus 1, and after 2 and before 3, suppose here we have 3, so after 2 we have a point t. So this guy h of t minus tau is basically varying in this area, and this is our x of tau. Okay, so the overlap that we are going to see, I will make overlap with, this is basically the overlapping part, and you see that overlapping is only between t minus 1 to 2. Okay, so now our integration, that is also gives us the output y of t from minus infinity to infinity, x of tau h of t minus tau d tau, that becomes equal to, from, again I'll write from, you can see that from minus infinity from minus infinity to 0, both of them are 0. Okay, from 0 to t minus 1, we have x of tau as 1 and h of t minus tau as 0, d tau, plus from t minus 1 to 2, x of tau is 1, h of t minus tau is also 1. And then from 2 to t, we have x of tau is 0 now, and h of t minus tau is 1, d tau. And finally, from t to infinity, we have x of tau is also 0, h of t minus tau is also 0, d tau. So finally, what we get here is only this part remains, rest all of the terms are 0. So we get here basically d tau integral over d tau from t minus 1 to 2, and that brings us to, you can see here that tau will come and we'll have t minus 1 to 2 here. So we will get here 2 minus t plus 1. So that will be 3 minus t. Okay. So we have y of t is equal to 3 minus t for t lying between 2 and 3. Okay. Now we summarize all the things what we have done. So basically, if we try to see that all the y of t's that we have obtained so far, okay, all the y of t's from the reason that t is less than 0, the first case was t is less than 0, then t lying between 0 and 1, then t lying between 1 and 2, then t lying between 2 and 3. Okay, so basically we'll have y of t is equal to, we have various values. The first one is when t is less than 0, then when t is greater than 1 and less than 2, then when t is greater than 2 and less than 3, then we have t is that is only the case, I think. We left t. The second case is when t is greater than 0 and less than 1. The third case is when t is greater than 1 and less than 2. The last case is that t is greater than 2 and less than 3. Okay. So when t is less than 0, we saw that this integration is giving us 0. When t was between 0 and 1, greater than 0 and less than 1, y of t was equal to t. When t was greater than 1 and less than 2, y of t was equal to 1. And when t was greater than 2 and less than 3, y of t was equal to 3 minus t. This is the comprehensive solution that we are, the total solution that we are having. This is basically value of y of t. Okay, so now I will try to plot it. This is better. So we have this as the value t, and this is y of t, and we have the points that are on the time axis, that is 0 and 1 and 2 and 3. Okay, so from 0 to 1. Okay. So basically that finds another. Okay, so this is one point and this is another point. Okay, so we can see that from 0 to 1, y of t is simply equal to t. Okay, before 0 it was just 0. From 0 to 1, this is t. From 1 to 2, this is simply 1. Okay, and from 2 to 3, this is 3 minus t. So at t is equal to 2, we can see that y of t will be having a value 2, and at t is equal to 3, t is equal to 0, y of t will be having a value at t is equal to 3, y of p will be having a value 0. So, and this is having a -1 slope here. So we get here. This is fixed. And this is what we get as a solution. Y of t here. This is 1.0, and this is essentially the convolution between two functions that are given as so it's a straight line, and so this is essentially the convolution between this was our h of t, this was our x of t, this was varying from 0.0, 1.0, varying from 0 to 1, and this was varying from 0 to 2. Okay, so when we convolute both of them, y of t that is obtained in this form. What we saw here was that we can see that you can simply see that we had moved. You can see that this is how we were moving h of p. This h of p is basically moving. If you look only into this function, you will see this h of p was first here, then it was moving to the right side. From the left side, from the extreme negative side to the right side, we are moving it. We moved it to this part, and then we saw the overlap. Initially we were keeping it on the left, then we saw the overlap, how much it is overlapping. Then we moved it to the right side. In this direction we moved it. We were moving it, and we were seeing the overlap. Then we moved it again more to the right side, and we were seeing the overlap. And this is essentially, so basically at h of p, and then we were moving it further to the right side, and we were seeing the overlap. Okay, how much it is overlapping. So essentially we can see that h of p was being moved, or it was being slided on the horizontal axis, and x of p was fixed. And while this move was happening, we observed the overlap that h of p is having over x of p. Okay, so that's all for today. We'll continue it in the next class. Thank you, everyone. Okay, thank you, everyone.